sharper than a thorn. Like a mouse he's spry and nimble when he grinds the corn. Like a bird he'll watch the wind and listen for the sound, which says he has the wind he needs to make the sails go round.
Hello and welcome to everybody. Today we're going to be carrying on with our open source Pi Pico weather station, and you'll remember that in the last episode we constructed an anemometer to actually measure the speed of the wind. Well, we're actually going to build the kind of, what do you call it, brother or sister to the anemometer. This time we're going to build an electronic wind vane, so this is actually going to measure the direction in which the wind is coming from. But before we do that today, we're just going to finish off with the anemometer because we didn't actually see it plugged into the Pi Pico and measuring some wind, so let's do that. You'll remember from last time that our anemometer here uses an optical encoder, so for every revolution of the anemometer it actually outputs 10 pulses. On the Pi Pico we've got 28 GPIO pins. Now GPIO stands for General Purpose Input and Output. So within the software we can actually configure any of those 28 pins to be either inputs or outputs, and in our case the pulses from our anemometer, they're going to be connected to GPIO input 5. Now it is very important that we only connect the inputs to a maximum of 3.3 volts. They're not 5 volt tolerant, so if we were to connect 5 volts to any of the inputs it would actually damage the microcontroller, and that would quickly get expensive. So whatever you do not connect a 5 volt supply to any of the inputs. Now the infrared LEDs and the photo transistors that I employ within the anemometer here, I'm actually powering them from a 5 volt supply, but if you look at the circuit diagram for this you'll see that I'm actually using some resistors to actually divide down the output from the photo transistors, so I'm dropping it from 5 volts to 3.3 using a simple potential divider. I've written some very simple software using MicroPython and I've downloaded that to the Pi Pico. Now the purpose of this software is to count the number of pulses which are coming from our encoder, and it's going to work out the wind speed based on that pulse count. Now for those of you that want to take a more detailed look at the software, remember all the software which is featured in these videos can be downloaded, so see the show notes where you'll find a download link. With the aid of this blowgun it's time to generate some wind, so let's give that a go. Well, I can't be sure of the calibration, but it certainly seems to be doing something, doesn't it? Now, although we're building a weather station in this project, the weather station part really isn't the most important thing. But more importantly, we've seen how easy it is to use microcontrollers such as the Pi Pico, and also how we can allow a microcontroller to see the world around it by connecting a variety of different sensors. So the incremental encoder here, it was actually capable of determining the rotation of a shaft. But when it comes to a wind vane, we're not so much interested in the rotation speed as such. What we actually want to know is where it's pointing. It is possible to measure the angular displacement of a shaft using an incremental encoder like this one by simply counting the number of pulses. So you can see that I've put a piece of red tape on the front of the shaft here just so you can see a start position. And you'll remember that the encoder wheel inside here, it has 10 slots in it, so it has 10 separate positions and will produce 10 pulses per rotation. So if we now to rotate this shaft through 180 degrees, we'd expect to get a pulse count of 5. So let's do that. And we have 5 counts. So we can determine that the shaft has rotated by 180 degrees. And if we continue to rotate the shaft by another 180 degrees, we're going to come back to the start, which is 10 pulses. Let's rotate it by 90 this time. So we're at 12 pulses, stroke 13. Let's keep going back to the 180 position. Now I was expecting that to be 15 pulses there, but obviously I've gone a little bit too far, or I've wobbled. And really I've just demonstrated the problem here in that when I was trying to rotate the shaft carefully, I've either gone a little bit too far or I accidentally pushed it backwards. Now it doesn't matter which way I rotate the shaft, the count value will always increase, so I'm actually going anti-clockwise now. So you can see the problem that we would have with our wind vane now, that it wouldn't matter which way the wind vane was pointing, the count value would keep increasing and we'd very quickly actually lose our position. Many of the problems of the incremental encoder can be overcome by using a quadrature encoder, and we've got an example of one of those here. And the main advantage of using a quadrature encoder is that it's direction sensitive. There are several different types of quadrature encoder available, and the one that I'm using today is electromechanical in nature, and it's the type of encoder you'll often find used in low-cost consumer-grade equipment, with a typical application of something like the volume control or tuning control on a modern digital radio. The encoder that I'm using is a free wire device, and one of those wires, which I've shown in green, is normally connected to the cog part which rotates. The other two contacts, which are often labelled A and B, they make contact with the cogwheel as it rotates. And typically you'll find those A and B contacts connected to the inputs of a microcontroller via suitable pull-up resistors. The rotating part of the encoder is connected to ground. The position in which I've stopped the encoder, neither the A contact or the B contact is actually touching the cogwheel, and the external resistors connected to the A and B contacts would be pulling them high to a logic 1. You can see that contact B is now touching the encoder wheel, so it's being pulled down to ground, and we can see we've got a logic 0. The A contact isn't touching the wheel, so at the moment that's still being pulled high to a logic 1. If we continue to rotate the encoder, you can see that both contacts are now touching the wheel, so both A and B will be pulled to ground and they'll present a logic 0 to the microcontroller. In the next position, the A contact is touching the wheel, so that's pulled down to ground and is a logic 0, whereas the B contact is no longer touching the wheel, so that's going to be pulled up high to a logic 1. If we rotate our encoder one last time, you can see that we've got back to where we started. Neither the A contact or the B contact is touching the encoder wheel, so both A and B will be pulled high to a logic 1. If we allow the encoder to rotate continuously again, you can see that it produces a bit pattern on the A and B contacts. Here on the bench I've got a quadrature encoder, and you can see that on one side of it it's got 3 connections. Now the middle connection, the middle pin, that's actually connected to ground, and then the pins on the left and the right, they're the A and B pins which produce the output pulses. If I just turn the encoder over, you can see on the other side of it we've got another 2 pins here. Now these are somewhat of a special feature because not only can I rotate the encoder, as you would expect, this actually includes a push button, so I can actually push it and I get a click like that, because that's useful for some applications. Maybe you want to scroll through a menu and then you want to choose yes or maybe no, so having a click built into an encoder control like this is quite a useful thing to have. Now just to stop everything floating around, I've taken a plastic container and I've gone ahead and I've installed our encoder just inside it like that, just to stop it moving around and give me some control over it. And then on the top of the encoder you can see that I've got a knob here with an arrow on it which we can actually turn in a number of different positions, and I put north, east, south and west on there. And as for the electrical connections between the encoder and the Pi Pico, let's take a closer look. So this black wire connects 0 volts to the centre pin common of our encoder. The A contact on the encoder is connected to pin 6 of the Pico input, and contact B is connected to pin 7. And finally this blue wire connects the push button on the encoder to input 8. I've also squeezed in a couple of 100 nanofarad capacitors, and they're connected between the A contact and ground and the B contact and ground, and I've added those capacitors to help deal with the problem of mechanical switch bounce from those A and B contacts. I've also connected a $5 logic analyzer because I thought that it might be interesting to have a look at those A and B pulses as we rotate the encoder, so let's do that. So I'm turning the encoder here in a clockwise direction. And let's zoom into our A and B waveform. You can see that the rising edge here of waveform A, it actually leads waveform B. So you can see that A is in front of B. Here's B lagging behind, and here's the A in front of it. Let's run that again, but this time we'll turn the encoder in an anti-clockwise direction. And with the encoder rotating in an anti-clockwise direction, you can see this time that the actual rising edge of pulse B, it's actually in front of pulse A. So not only is our Qaudrature encoder capable of producing pulses which can be counted, we can also examine the rising and falling edges of those pulses to determine the direction, and if we know the direction we can either add pulses or subtract them. So let's look at some software that can do that. Starting off with our title block here, I always like to include the file name and also provide a description of what the software is going to do. In this case we're going to read pulses from a 20-step Qaudrature encoder, and we're going to print a direction to the screen. I always include a software revision and a date that I created it, and also the target hardware that the software is going to be running on. In this case it's a Pi Pico, and the microcontroller is the RP2040. The author is me, All the Gear No Idea. And in the case of this video series, all the code is open source, free to use and modify. And for those that want to play along at home, remember there's a link in the show notes where you can download it. However, I will make the caveat that I've only been learning to write MicroPython for just a couple of weeks, so I'm sure that you can improve on what I've written here. As always, we start off by importing any libraries that we're going to use, the most important one here being the pin library, because that tells the Pi Pico about the inputs and the outputs that we're going to use. The next thing that we do is configure those inputs, and you can see here that we've got the home pin, which is the push button on the encoder. That's connected to pin 8. The A pulses from the encoder are connected to pin 6, and the B pulses are connected to pin 7. You'll remember that the encoder that we're using has a common ground connection, so I'm going to use some pull-up resistors which are actually built into the RP2040 microcontroller. I declare any global variables that the software is going to use next, and then we come to our first function. And again, important to say what this function does. And in this case, it's actually going to print the wind direction to the screen. So you can see we've got those directions listed here because we're going to use a list to actually decode the pulse count from the encoder and turn that into a text string. Once we've decoded the count value, we need to print it to the screen, so I do that here, and I also multiply that count by 18, and all I'm doing there is I'm actually providing an output in degrees. Now the main part of the software is contained in this while loop, and of course this while loop will execute forever because it's while true. I then tell the microcontroller to read the inputs which are connected to the A pulse and the B pulse, and I actually store them into some values here, so one's called new A and one's called new B. I then check to see if the encoder position has changed, and the way I do that is by comparing the new pulse A value by the previous pulse A value, and I say if they're not equal to each other then something must have changed. I then look for falling edges for the A pulse and the B pulse, and depending on which edge falls first I can determine what direction the encoder's been rotated in. And if the encoder has been rotated in a clockwise direction, we add 1 to the count value, and if it wasn't in the clockwise value it must have been in the anti-clockwise direction, in which case we decrement 1. Finally, within this function we say that the old pin value is equal to the new value, because what this will do is is, if the encoder hasn't changed position, if old pin doesn't equal the new pin, next time we execute this code it won't actually do this, it'll just drop straight through. Next I'm going to do some scaling of the encoder count value. So I say that our encoder count can be allowed to be between 0 and 19. And the other thing that I'm doing here is I'm preventing the occurrence of any minus numbers because they could be more difficult to deal with. So we're always going to get a plus value from our encoder ranging between 0 and 19. Earlier we saw the function that prints a wind direction to the screen. Now I only actually print that wind direction if the encoder has changed position, so I use an old count and a new count value, much the same as we did previously. And I've also added another feature which allows us to set the count position to 0 by pressing the button on top of the encoder, and we'll talk about that more later. So let's take our Qaudrature encoder for a spin. So we're pointing north at the moment, let's go all the way around. Well, that's a good start, we're still pointing north. Let's go south. We're pointing south, but the big question is, will it go in the opposite direction? Because remember, our incremental encoder, that could only count upwards, so if we've done this right we should be able to count down as well. So here we go, and there we go, back to north. So you can see that having this Qaudrature encoder, it does actually solve a lot of the problems that we had with determining what position we're pointing in. However, we're not quite out the woods yet, because in order for our encoder to keep accurate position, it must remember what the previous pulse condition was. It has to remember whether the A waveform was leading or lagging the B waveform. The other problem is that we've also got this count value that we're building up. And the problem that we're going to face is that we're going to have to remember the state of those pulses and the count value using the Pi Pico. Well, things happen, don't they? So if I just unplug the Pi Pico now, it's going to lose power. As soon as it loses power, that count value and the previous pulse information, that's going to get lost because that information was stored in RAM, and that RAM gets deleted when the power's removed. So let's plug in again. And unfortunately, it thinks we're pointing north because that's what it was expecting. And that's a problem because when this weather station's installed on my roof, I've got no way of actually telling it which way it's pointing, and at some point it will forget. So if I turn this back to north now, well, it's actually saying west because it's lost its index. It hasn't got a datum point. It's forgotten where it was in effect. Now remember I mentioned the push button before. Well, what I can do is I can actually zero the count. So if I can press that button, it now knows where north is again. And if we can go backwards and forwards, and we're back where we were, we're working again. But at some point this is going to lose power and it's going to forget where it is. Now there is actually a relatively straightforward solution to this problem of losing count that can be employed for some systems. So what we have to do is to add a reference point, which works in the same way as pressing this switch here, which allows the count to be 0. So you can imagine we could add a reference to the north here, and that even if it started up at east position, as soon as the wind blew round to the north, this system could zero itself, and then it would be okay again, until which point it lost power. And that could certainly be a solution. The only problem is, if for whatever reason the wind never blows from the north, you could actually be out of alignment here. You could be providing the wrong indication and you wouldn't actually know it because you hadn't redatumed the system, you hadn't set the reference point. So really what I would like to do is I'd like to use some form of encoder that isn't reliant on keeping this count value. It's not reliant on the microcontroller remembering it. Well, there are types of encoder that can do that, and they call those absolute encoders. So let's look at those now. The simplest absolute encoder that I could come up with uses just 4 mechanical switches, and those 4 switches are operated by a cam here, and you can see that the cam has a lobe on it, and the lobe is actually designed so it can actually operate 2 switches. So although you may think having 4 switches we can get just 4 positions, we can actually get more than that. We can get 8 positions because we have each switch being individually operated, and then what we can also do is we can operate a pair of switches like that. We've got each of our 4 limit switches here connected to the inputs of the Pi Pico, and I've written just a few lines of software to read those inputs, and based on which inputs are switched on and which inputs are switched off, we print a message to the screen. I've also got the Pi Pico controlling these 4 LEDs. Now these LEDs, these actually correspond to each of our limit switches. So you can see that when the north limit switch is activated here, and then if we move to the northeast position, we've actually got 2 limit switches activated. So we've got the north switch and the east switch activated both at the same time. So you can see we've got both switches activated. Then we'll just move it on, so we've just got east, southeast, south, southwest, west, northwest, and finally back to north again. You'll remember that from looking at our incremental and quadrature encoder that those systems relied on counting steps, and we also needed some way to produce a datum or a reference point from which we could actually zero our count. But an absolute encoder doesn't suffer from either of those problems. So let's just move it to the east position. And I'm just going to disconnect the power from the Pico. And let's plug it back in. And after restarting the Pico, you can see that it is actually still creating the correct position. Now it also doesn't matter if the position of an absolute encoder changes while the power's switched off. So let's confirm that. So let's switch off the power. Let's move the encoder to the south and restart. And again the Pi Pico has started up correctly indicating the south position. So this simple 4-switch CAN box arrangement does seem to suit us quite well for our weather station, in that we can actually indicate fairly accurately each of our wind direction positions. But unfortunately there is some problems with this mechanical design. The first problem that we have is actually quite a lot of mechanical friction here, and I can actually feel it pushing against the cam as I rotate it. Now I don't think that would work too well for our weather vane, because if the wind wasn't blowing very strongly, I think the friction would actually stop the cam from operating these switches. Now I'm sure that it's possible to actually buy switches that require less activation pressure and they wouldn't introduce as much friction into the system, but unfortunately I don't have any of those to hand. I think the other problem that we would have with mechanical switching is simply one of wear, that these switch contacts would actually get worn out from constant activation on and off. We can probably quite easily improve on this arrangement by simply swapping out those switches for some switches that are actually non-contact, so let's do that. And so I've simply replaced our mechanical clickety-clack switches here with 4 Hall effect transistors, and rather than a cam acting on the switches, what I've done is I've actually glued a number of little magnets onto the cam here, so as soon as the magnetic cam becomes close to any of the transistors, it actually switches it on. And because the cam no longer makes any physical contact with the switches, we've got no friction, we've got no wear, and we can actually move an awful lot faster if we wanted to. For some of you greybeards out there that won't have anything to do with this digital shenanigans, the Pi Pico has another trick up its sleeve, which comes in the form of 4 12-bit analog to digital converters. Now I say there's 4 analog to digital converters, but there's only actually 3 of them we can use ourselves, because one of them is used on the Pi Pico board itself to measure temperature. So all we need to do is take a potentiometer and we connect it as a potential divider here, and we feed the wiper, the middle of the potential divider, we feed that to the analog to digital converter, and then as we actually turn the shaft, we'll actually vary the input to the Pico between 0 and 3.3 volts. Now remember, I did mention earlier, it's very important that you don't connect the Pico to more than 3.3 volts, so you're going to do some damage. And it really is very easy to then just write a few lines of software. We can get the Pi Pico to read in the voltage from our potentiometer, and then we can just do some scaling and some comparison with some thresholds, and we can use that to print up the wind direction on the screen. So let's just give it a rotate. So that really does seem to work quite well. But I'm sure some of you have spotted a problem with this arrangement. So let's assume the wind is going to blow from the east now. Now it's going to blow from the south, and it's going to blow from the west. Oh, but unfortunately we can't measure further than west because the potentiometer has actually reached the end of its travel. However, don't worry, because it is actually possible to buy potentiometers that do rotate through 360 degrees. Unfortunately, I don't have one, but you can buy them. Now, some of you might say, of course, you could just use something like this, a 10-turn pot, but the problem is, eventually, you're still going to wind it to its end position and you're going to come up against the stop. Well, you probably won't be surprised to know, having looked at incremental, Qaudrature and a whole range of absolute encoders, I didn't actually end up using any of those. And thanks to a time machine paid for by my Patreon supporters, I've actually popped back from the future to show you what we built instead. So really what I've done here is I've based our new weather vane, I've based it on most of the common components that we used in our anemometer. So you can see that we've got the same platforms and we've got an encoder wheel, but this time we've got a lot more photodiodes and phototransistors. So let's take a closer look at what we've built. We've got a 3D model of the anemometer that we drew up in the last episode using Fusion 360. And for those of you that want to play along at home, remember that all the Fusion 360 and step files are available to download, so see the link in the show notes. Let's remove the slotted disc encoder wheel used on the anemometer. And for our absolute encoder, we're going to need more phototransistors and infrared LEDs, so let's add them now. And we've now installed the slotted wheel that we're going to use for the absolute encoder. We've got a number of slots in our absolute encoder wheel, and depending on the position of the wheel, some of our phototransistors are going to be either exposed to infrared or not. And those 4 phototransistors are going to produce a bit pattern which is dependent on the wheel's position. So let's reinstall our infrared LEDs now. And we don't need the parts used for the anemometer, so let's get rid of them. And here are the wind vane parts. For absolute encoders, there's a number of different ways we can set up the slots in the encoder wheel. And the one shown here is a binary weighting. So depending on the position of the wheel, some of the phototransistors will be exposed to infrared and some will be hidden from it. And with the wheel in its current position, all the phototransistors would be exposed to the infrared LEDs and they'd be switched on. So in which case we would have 1 and 2 and 4 and 8. And that would produce a code equating to the number 15. Let's rotate the wheel now through all its positions and look at the binary output from the encoder. Unfortunately, there is a problem using these natural binary codes in that physical switches are not ideal, and it's very unlikely that the switches will actually change state synchronously with each other, and you'll potentially get a problem when 2 or more of our switches have to change state at the same time, and due to manufacturing tolerances, 1 or more of our switches is likely to lead or lag the other switches, and that will produce spurious position information. The way in which we can overcome this problem is to rearrange the slots in our encoder wheel, and we do this to ensure that we only ever get any of the bits transitioning just one at a time. And there are several non-binary codes which we can use to achieve this. The coding system that I'm using is known as reflected binary, and it was invented by Frank Gray of Bell Labs in 1953. And you can see as our grey code wheel rotates that we only ever get 1 bit transition at a time. Now at first glance the output from our grey code encoder doesn't appear to be logical in that it produces almost what looks like a random pattern of bit changes. And each bit pattern is unique for the wheel's position, but we do have to decode it to produce more logical numbers. that looks like it's working okay. Well, as you can see, I've gone ahead and I've actually connected all our photo transistors here, and I've also tested them, so I know that they all work. So all I have to do now is got to install the infrared emitting diodes, and you can see I've got the wires just looped out here. So let's do that now. So let's go ahead and install our LEDs. Oh, that one seems a little bit tighter than the others. In a perfect world, I probably would have wired up all of these diodes in series, but unfortunately the volt drop across each of the LEDs, it's just too high to run them from a 5 volt supply, because it would actually just about exceed 5 volts. So the way I'm actually running this, I've actually got 3 of the LEDs connected in series, and then I've just got one on its own. So we are now near completion of our weather vane, so let's just go ahead and do the final assembly, and then we can give it a test, which hopefully that's going to be the exciting bit. Now we really don't have very much to do, we've just got to install these boards which we assembled, and then what we've got to do is just install our grey code encoder wheel, so let's start doing that now. This is designed to be just a fairly tight push fit. Yep, it is going on nicely, that. And there you can see that our infrared LEDs are actually lining up very nicely with the slots in our grey code wheel. And let's give our weather vane a bit of a spin test. Let's see how well balanced it is and how low the friction is. And talking of balance, I've got to admit I have cheated slightly, because on the lathe I actually made the little counterbalance pointer here on the end of the weather vane. Now of course we could have done it in other ways. We could have maybe got some M4 nuts and glued them on, stacked them together to make some weight up, but it only took me a couple of minutes to do this on the lathe. But I did have another idea. I did actually try wrapping some solder around the end of this rod, and then I made a little plastic cover over it, but actually I think that this piece of brass just looks a bit tidier. As you can see, I've taken our weather vane and I've connected it to the Pi Pico. Well, of course this is a little Pi Pico down here. The rest of the board really is just a development board, which it makes it much easier to actually connect things together. So it's quite a good idea to get one of these if you're going to be playing with the Pi Picos. And the outputs from our photo transistor are actually connected to 4 of the inputs on the Pi Pico. And the 4 inputs that I'm using input 6, 7, 8 and 9. You can also see that we've got an LED illuminated here. Now this is actually also connected, but this time to one of the Pi Pico output pins, because this is representing the drive to an electronic switch. So we're actually going to use that to switch on and off the LEDs which are installed on here, because we don't want to be burning power all the time. These LEDs in here, they're going to take about 40 milliamps. That's going to run our battery down. So basically we're only going to switch those LEDs on when we're actually going to take the wind direction measurement. You can see that I've taken an indelible marker and I've put a little cross on the front of the wind vane box here because this cross represents position 0 on the encoder wheel, and what I've done is I've set the software up so that position 0, that's going to equal north. So let's just move it to the north position and then we'll run the software. And now we've started the software, you can immediately see that we're actually indicating position 15 on the encoder wheel, and we've actually decoded that number 15 and we've translated that into the word north, and you can see we've printed both them to the screen here. And it's worth mentioning here that we didn't have to do any kind of indexing to make this encoder work, unlike our incremental encoders. The fact that we've used an absolute encoder, it delivers its position from a cold start. We know exactly where it's pointing. Let's rotate our weather vane slowly now and have a look at the output from the encoder. And at the moment we can see that it's pointing north, which is actually position 15. Now position 15 and actually position 0, they're actually both pointing north. So let's just move it slightly to one side. So there we go, we're still pointing north, but now we're at the 0 position on the encoder. Let's keep turning it. Okay, we're northeast at position 1. Also northeast at position 2, let's keep going, east at position 3, east at position 4, southeast at position 5, southeast at 6, south at 7 and also south at 8, southwest at 9, southwest at 10, west at 11, west at 12, position 13 northwest, 14 northwest, and now we're going to go back to north. There we go, north. Let's finish off today by taking just a quick look at the software, and I'm sure this code could be much improved on because we didn't have time to paint it or build it to scale. Now at the top of the code here, of course, we've got a title block because in a week's time you'll have forgotten how it works and what it does. And then we're going to import the libraries that we use, which are simple for the pin and the timers. We're then going to define the GPI inputs that are going to connect the encoder to our Pi Pico. Our encoder has 4 optical switches, so it has a 4-bit output, and I'm connecting it to pin 6, which is the least significant bit, pin 7, pin 8 and pin 9, which is the most significant bit. And to keep all of those inputs under control, you can see that we've defined the internal Pi Pico pull down resistors, and they equate to about 60 kiloohms. We then define an output which is going to be pin 10 because we're going to use this pin 10 output in the future to turn off the power supply to the LED lamps within the encoder. I'm now going to declare any global variables that I may be using, and there's just one called old position. The old position variable is going to be used later on in our code, and it holds the old position from the encoder, and we're going to use this to stop the output from the encoder, the same output being printed multiple times to the screen. The software for reading the position from the encoder and then displaying the wind direction is split into 2 function blocks, and the first of those function blocks is used to get the positional information from the encoder, and I've actually called that get wind direction. Our encoder is 4 bits, so that gives a possible 16 positions. So if we take our 360 degrees and divide that by 16, we get a resolution of 22.5 degrees per position. Now, a quirk of the RP2040, which is employed by the Pico, is that we can't easily read in a single byte of information, or you can't read in parallel bits. That isn't actually true, but it's certainly not the most straightforward thing to do. So what I'm going to do shortly is I'm going to read all the bits in individually, one at a time, and then I'm going to assemble it into a string. As we saw earlier, the output from our encoder, it's not binary and it doesn't count up in a logical sequence of bits. You can see we've got what looks like a random list of numbers here which goes between 0 and the value of 15 in no particular order. So we start at the first position here, which is actually 0. The second position would be 1. The third position is a 3, but the fourth position is a 2, and a 6 and a 7. So we're going to decode our grey code using this lookup table. I said earlier that we have to assemble our individual bits from our encoder into a string, and I've named that string here. We're going to call that grey code. Now of course, before we take a reading from our encoder, we need to switch on those infrared LEDs. So that's what I'm doing here. Now the Pi Pico can only output about 10 milliamps from each of its output pins. So what we'll actually do in the real world, we're going to use the 10 milliamp output to switch on a transistor, and that transistor in turn is going to switch on those LEDs. And then we're going to wait for 10 milliseconds because we've just switched on those LEDs. We may have a little bit of a power surge, and I'm just waiting 10 milliseconds for everything to just settle down before we try and read our grey code. The first if statement here is going to read the most significant bit of our grey code, and I've got that here as grey code bit 3. Now if the slots in our encoder wheel line up correctly with the photo transistor for bit 3, what's going to happen? We're going to get a 1 written to the input here of bit 3. Now if the slot doesn't line up, the light will be blocked and we're going to get a 0. So if our encoder's output is a 1, what we're going to do is we're going to take a 1 here and we're going to stuff it into the first bit position of this grey code. If it happened to be a 0, we'd stuff a 0 into the first bit position. We then repeat the same thing for bit 2, bit 1 and finally bit 0. Now as we shuffle those bits in, they actually move from right to left. So by the end of this, we're actually going to have stored in grey code, we're going to have 4 bits of information. So we've got all the information we need now to produce our grey code value, so we may as well switch off those LEDs because we don't need them anymore. So here I'm doing that. Now finally I'm going to take our grey code byte that we've just filled up and I'm going to take it up here and I'm actually going to decode the value that's stored within it, and I'm going to decode it by comparing it to actually each of our grey codes. So I'm going to say, is the bit pattern a 1? Is it a 3? Is it a 2? Is it a 6 or 7? Now depending on what the value is, we're actually going to get a number, an index number returned from this list. So we're going to pattern match it, and if for example it was a number 7, what we would do is we would return the number 0, 1, 2, 3, 4, 5. So we're going to decode 7 into position 5 and return that from the function. So our first function here, which is get wind direction, we use that to read in the value from the encoder, and then we had to decode it into a position value. We're now going to take that position value and we're going to use a second function which is called display direction text. So we're actually going to print out the position, which could be 0, 1, 2, 3, etc. going all the way up to 15, and we're also going to print the direction, which could be north, northeast, east, southeast, south, southwest, etc, etc, all the way until we come back to north. Now you'll remember that previously we declared a global variable called old position, and to make use of that variable within our function display direction text, we have to specify it as being global so we can import it into the function. So that's what I'm doing here, so we can use it. And then we simply have an if statement, and what this does is it looks to see if the position information has changed from the old position, and if it has, it prints that position to screen and then it updates old position with the current position. So what this does, it stops the text just constantly scrolling because the screen's only updated when the position changes. For our weather station, I only plan to get the wind direction just a couple of times a minute. However, just for fun, I connected up an oscilloscope and I connected it to the infrared LEDs, which are switched on at the start of the measurement and switched off at the end of it. And I found that each of the encoder read cycles was taking about 10 milliseconds. Or to put it another way, we were taking 100 samples per second. Now we can actually sample very much faster than that if we want to, because at the moment my program has a 10 millisecond delay, which I just allow for the LEDs to settle down once they've been switched on. but we can remove that delay, and when we do, the program will execute an awful lot faster. And with that delay removed, our encoder sampling period drops from 10 milliseconds to 0.5 of a millisecond. So that means we can actually take up to 2,000 samples a second if we wanted to. Well, I think for today that'll do, and I hope to see you very soon for part 3 of our weather station project. Bye bye for now.